Yeah, hello everyone. Good morning. So I'm Martin. I'm a cryptography engineer and security researcher at 𝒫𝔩𝒫𝔬𝔫𝒦, and I would like to speak today about our work on explaining and democratizing access to Plonk. So I hope you all heard about zero-knowledge proofs? Yes. Okay. So just quick refresher. And this is the typical setting in zero-knowledge proofs, right? So you have a prover, which is typically not trusted. He can be malicious. And you have a verifier, and the prover wants to convince the verifier that some computation, some statement on some secret is true. And the verifier wants to check that. And usually what you care about here is obviously that the prover cannot craft fake proofs that the verifier would accept, and also that the prover, when he proves something that is true, the verifier will accept it. And there's also a notion of privacy, so that witness can be secret on the prover. So that's the very high level view of zero-knowledge proofs. And as you know, there's been in the last few years a lot of applications, interesting applications of zero-knowledge proofs to blockchain. So for instance, rollups, for instance, identity verification, CKVMs, etc. But if you have heard about primitives to build these proofs, right? So has everyone heard about Plonk? Maybe, sometimes, yes? Have you read the paper? Yeah. Okay, so Plonk is a very impactful protocol, right? So this is 2019, circa, the paper. And we thought this was interesting because it has had a lot of impact. Obviously, there are several protocols that somewhere, somehow use Plonk. There's also a lot of variants of Plonk that, Plonk has inspired optimizations. So it's a very popular zero-knowledge primitive. However, it's a bit hard to understand what is going on. There's a lot of tutorials and there's a lot of good material out there, but we thought there was something missing. Essentially, if you try to read the paper is very dense. It's very math heavy. And even if you're into crypto, and even if you have read papers, there's a lot going on, right? If you look at implementations, there's a lot of implementations, right? Like Helio 2, which we think is one of the cleanest. They already diverge from the paper a bit. So they already optimize a bunch of things, and they do things in a very optimized way. So it's difficult also to reverse engineer the protocol from the implementation. So our goal here was, can we design a tutorial that kind of bridges this gap? So the challenges here are several. So on the one hand, you want to have a tutorial, or our idea was we want to have a tutorial that is realistic, that is not super far away from the real protocol, but that is tractable, that you can grasp. So one of the criteria was, or one of the discussion was, should we use real fields, real curves, elliptic curves where we can do real crypto, or should we use like toy examples? There are some tutorials that try to give the intuition on a toy example, but we thought, okay, that's not what we want to do. We want to do something closer to the actual protocol. And we also wanted to have something that is didactical, that is incremental. So I will show you a quick demo, and hopefully I will inspire you to do the full tutorial. We won't have time to do that today, but I'll just give a quick intro. Okay, so we have a running example in our tutorial. And you will see in many CK tutorials, there are very minimalistic running examples. This one is a bit artificial. So what we have here is essentially up to this gate is Fibonacci. So this is the fourth Fibonacci number, right? So you start with 0, 1, then 1, 2, 3. And then you have a square. So you just have multiplication with itself. So this is the fourth Fibonacci number squared. And the nice thing is that it's a relatively small circuit, but for Plonk, it already has a lot of interesting ingredients. It has both addition gates and multiplication gates. So we can do interesting, actual, realistic instantiations of the protocol. And originally, I mean, at the beginning, we don't insist too much on the privacy side of Plonk. we're going to focus only on the correctness, which is kind of the 90% of the protocol. So that means our scenario is, let's assume that there's not a prover, but let's say like a processor, like you delegate this computation to the cloud or to some powerful server, and you care as a verifier whether the result of this computation is correct. So is this result, if you just look at this and a proof, is this really Fibonacci number 4 squared? So it's more like a correctness emphasis from the beginning, so that we don't overwhelm the student too much. But we go all the way. So in our tutorial, I'll show you in a second, we really want to go from tables and circuits at a very arithmetic fundamental level, all the way through polynomial constraint systems, zero quality tests, commitment schemes, KCG, over the real curve using real pairings, Fiat-Shamir, and proof and verification. So there's a lot of building blocks here. That's why we use this kind of Lego analogy through the visuals. But let's have a look. I mean, that's enough introduction, I guess. So this is Munich Habenhof. I was trying to get here in time. So essentially, there's a website. This is plonk.ckSecurity.xyz. And here, there is like a plain HTML version of the tutorial. And you can see like the same example I was talking about. And the idea is that the tutorial interleaves like Markdown with LaTeX, so with formulas and explanations, and some exercises. And the exercises have a little bit of Python that you have to complete. In this static version, you are free to implement things however you want. It's just a guide. We thought it's useful for people that maybe don't want to solve this in Python and Sage. But the whole tutorial is built, and I solve it using Python and Sage. So it's recommended that you do it that way. And I will show you the notebook in a second. But just to give you an idea of the static version, you can see here on the left-hand side the different sections that we discussed. And you can get a feeling of what's going on. So typically, we give explanations and some test cases. Sometimes they are like code, and sometimes they are more like actual numbers. So let me see here, for instance. So for instance, here we explain interpolation of the real field of BN 254. And if you implemented things correctly, like if you interpolate things correctly, then we give you like a test case that's deterministic that you can check against, like to see if you're doing okay or not, right? And the goal is that if you do this step by step, and you go through all these different sections that we discussed, right? So at the beginning, it's going to be like a lightweight protocol that we're going to recap here at the end of this section, and it's going to be something like this, where you just have, this is a bit small, let me make it bigger if I can. So essentially, you have the processor and the validator, and you start computing the Fibonacci circuit, and then you compute some constraints that are quite simple. You share the polynomials in plane, and then you check some values on the validator. So this is not yet Plonk, this is proto-Plonk 0.1, but this gives you an idea of kind of the dynamics, and we build on top of that towards the real protocol. And at the end, I'm just spoiler alert. So after a lot of work, and if everything is correct, we give you a verification function that if you implemented the proof correctly, this verification function will check all the steps, and you should pass this function. So this is kind of your oracle to know if you did well, but of course you get feedback along the way. That makes sense so far? Cool. And this is one way. And the other way is like you see here, download notebook. So on the web page, there's a link. And if you do that, then you get this kind of Jupyter notebook that runs on a Sage kernel. So you need Sage installed, but you can also run this on the cloud. So for instance, there's a CoCalc that you can use for this, and there's some links here. And the nice thing here is that you can interact with it, right? So for instance, let's have a look at the first exercise. So the first exercise talks about, seeing the circuit as a table where you have 3 columns, the left input, right input, and output, which corresponds to, per gate, left input, right input, and output. So as you can see, the first 3 gates are additions, and the last gate is a multiplication, right? So the first exercise says, let's try to convert this into something, well, that we can then write code on. Is this okay? I hope you can see this. So exercise 1 says, consider the set of indexes from 1 to 4 as the vector I given below represent the left and right columns as vectors, and the output vector is vector O. So there's one small detail that you may notice here. I'm not sure if this is big enough, but you see the indexes are 1, 2, 3, and 4. Indexes are super important in Plonk. At the beginning, we use natural numbers. Later on, we're going to use a multiplicative group, which is a bit deeper math, but this has advantages for the protocol that will be evident later for the permutation argument. But Python doesn't support, so Python uses indexes starting with which number? 0, right? So we cannot just use vectors in Python to represent the values, because otherwise we will mix up the indexes. So we use a dictionary where we have the indexes from 1 to 4, and then the values as the values of the dictionary. This is a little bit, weird, but it's important, because it's really important that we start with 1. So for instance, if I try to run this cell, so I can execute this cell, of course, this is not valid Python because there's something missing, so yeah, invalid syntax. The idea is that we fill that, that next column. So we have the first column, which is values 0, 1, 1, and 3, right? 0, 1, 1, 3. So we are asked to do the same for 1, 1, 2, 3, and 1, 2, 3, 9. But let us just suppose that we didn't understand the exercise and we're just doing something that compiles, and I'm just going to copy the same column 3 times and see what happens. So if I do that, of course, here there's no test case. This works. But the next exercise, which introduces a constraint system. So very important concept in zero-knowledge proofs is this arithmetization, where you just don't have a table, because a table is a table, but you have a relationship between the values, because the circuits are glued together, right, in a certain way. So you know that in Fibonacci, it's very important by definition, right, that the right input of the first gate is going to be the left input of the next gate. And you know that the output of the first gate is going to be the right input of the second gate, and so on. So you have these equivalence classes between these numbers, right? And then at the end, we have this weird thing that we have the square. So we have a weird 2 wires that go from the output to these numbers and then here. So how do we define these constraints? So at the beginning of the tutorial, this is going to be very ugly and very ad hoc, but this is on purpose. Because one of the contributions of Plonk is to, I'm not sure if it's completely a contribution of Plonk, because Plonk builds on top of things that already existed, but one main building block is this permutation argument that you may have heard, where this is done in more generality, but it's quite hard to understand. So we start with something simple. What is something simple? So something simple is, well, this is not, I'm not sure if this is too simple, but this is one mathematical way to see it. It looks scary, but it's not, right? So it's just the left input in position 1 is a 0. The right input in position 1 is a 1. That's the public values of Fibonacci, 0 and 1. And then you have things like this. The left input plus the right input should be the output for Fibonacci, right? So just addition gates. But this doesn't hold for all indexes, because the last index is a multiplication. And then you have what we discussed before. The left input in the row plus 1 is going to be the right input in the previous row. And the right input is going to be the output of the previous row. So this is written just mathematically like this. And then at the end, we have the constraints for the squaring. But the point here is that if you would convince the verifier that all these constraints hold, and that these two values, which are part of the constraints, hold, then the output is going to be this number. So it's the computation of this circuit. So this is very important, because the whole idea of zero-knowledge proofs builds on top of this concept of convincing the verifier that we executed some correct open public circuit. So exercise number 2, let's see if this works. We are already given 2 constraints implemented as example, and the exercise is to implement the other 3. So constraint 1 was the first two values for the first gate are 0 and 1, and constraint 2 is the addition gate constraint. because we cheated, remember, we just copied the column, so I expect this not to pass, but let's see. Okay, so if we execute this, then we get an issue with this assert with the first one, because this doesn't hold, right? So the first left input and the first right input are not 0 and 1. Let's have a look at what they are. So because we just copied the values, right? So we had 0 and what is the first right input in this wrongly implemented example? Also 0, right? And it should be 1, right? So let's fix that. So let's fix that, and then we go back here, and we run this again. Now we have a different issue, right? Now we pass the first constraint, but the second constraint doesn't hold. The second constraint says, well, the left input plus the right input should be the output for the first 3 gates. And of course, because we just copied the values, this doesn't hold, right? So how we would fix this? Well, the ideal way would be to copy the actual values. So let's do that. So this was 1, 1, 2, and 3 for the right column, right? 1, 1, 2, and 3. And for the output, it should be 1, 2, 3, and 9. So let's see if we now pass this. No. We still have a mistake. Right. So it should be 1, 2, 3, and 9. Let's check 1, 2, 3, and 9. Thanks. So now we passed. So now we don't get any complaints from the asserts, and this works. So in the interest of time, I'm not going to, just going to give you some stats on what we did and some further overview. But I hope that you get the feeling, and I hope you can appreciate that this is nice because you can actually kind of touch these objects. You can actually see what the values of the polynomials are. You can actually see what is going on in depth. So we have, like these exercises, we have 24. So we just did 1 and 2 partially. 2, we're missing a little bit. And we have 61 explanation cells divided on these 5 major learning modules. And maybe just quickly, we wanted to make this very realistic. So for instance, for KCG, which is a polynomial commitment scheme, we had a choice to make. For these polynomial commitment schemes, it's important. Have you heard about cryptographic pairings? Does that ring a bell? Well, it's an important construction in cryptography that works over elliptic curves that has a certain interesting mathematical property that is being exploited here for KCG. But unfortunately, this whole thing, just explaining pairings, is like a whole topic. It's like a book. Actually, there's a link here to a book that is like 300 pages just on this topic. So this is kind of a rabbit hole. So what we did was we didn't want to overwhelm students with this, right? So what we did is we give you a library that is here on the files that you share that you don't have to see. If you can see it if you like, where we have actual implementation of an extension that is needed for these things to work. But this is a bit like, as I said, like a topic on its own. So you can just import it, and we give you the code so that the pairing works. And you're asked only to verify that this simple algebraic constraint hold over this pairing. And because this is done on Sage, we already have a library where we can use Sage for the pairings, and we're guaranteed that this is implemented correctly. We don't have to re-implement it. If you look at some implementations of Plonk, they actually re-implement the whole thing, and that's very, very hard to understand. So, right, and you have the test case where you can see what is going on and what should happen, and so on. So it's hopefully realistic enough. It's very, very close to the paper and to many implementations, but it's a bit gentler, so you go step by step. So we have, so for your information, so this is public. You can have a look, you can download it, you can write us if you have feedback. We already used this here at TU Munich for a course on zero-knowledge proofs, where they already had seen the theory, just to show the exercises. So we did 2 sessions of 2 hours where I was going through the solutions. So I was already going at speed. But I think this was a good exercise to validate what we have done, because people appreciated it, and hopefully some of you, if you're interested in this, can also have a look and let us know how it went. Right, so with this, I'll conclude. So this was an introduction to our tutorial. We hope this helps learning zero-knowledge proofs in depth, but also at a good pace. So thanks for your attention, and I'm happy to take your questions.